In this next video on calculus, we'll be looking at practical application. Before we start, just as usual, to remind you on how to do mathematics, so number and copy the examples and ask your tutor or teacher if there are any steps that you do not understand. Number the questions, and unless you have the ability to get fit while watching someone else run, you must do the questions on your own before watching the answers. Mark your answers, and if it is incorrect, write down the corrections and make sure you understand where you went wrong. This will enable you to do better the next time you attempt a similar sum. Now we're going to get started by looking at what the first derivative practically means. Now the first derivative of a function is the rate at which the function or the value under question is changing. So always remember that when you're looking at a question, to practically think about what they are asking, and then think about what is changing and how fast is it changing. So if we look at this example 36, the path traveled by a meteor can be traced using the formula st, where st is the distance in meters that the meteor is from the Earth, t seconds after being detected. Okay, so A says determine the velocity at which the meteor approaches the Earth when first detected. Okay, so velocity, what does velocity mean? It means velocity is how fast is the distance changing. So velocity is the rate of change of distance. Meaning, if we want to use our function to answer this question, we need to get the first derivative of our function. So if I have for A, if I say st, the first derivative of s in terms of t, that's going to be, so this is a constant that falls away. Then we just have negative 600, because the t also falls away. 1 times by negative 600 is just negative 600, and then minus 0.6 t to the power of 2, because that's 3 times 2, plus, and then we have this this times by 5, so this would basically be 10 to the power, let's say that's going to be 10 times by 10 to the power of negative 3, so that gives us 10 to the power of negative 2, I believe, t to the power of 4. Okay, so that's the first derivative. Now, if we look at the rest of the question, it says the velocity, but where? The velocity at which the meteor approaches the Earth when it was first detected. So first means the time was immediately. So when the time is immediately, it's going to be where t equals to 0. So all I do now is basically just substitute in t equals to 0 into this first derivative that I calculated. So I have minus 600 minus 0.6, put it in, plus 10 to the power of negative 2. Alright, so this basically, these two terms will then fall away, and we are just left with negative 600. But now it's in meters, and then this is then going to be meters per second. T is in seconds, so the velocity is going to be meters per second. Alright, so B. Show that the meteor will collide with the Earth at t equals to 10 seconds. Now, what we're basically going to do is, if this is the distance, a collision would mean that the distance would be 0. There'd be no distance between the Earth and the meteor. So what we're going to do is we're going to substitute in the time 10 into the original equation to see what the distance is, because that would show us how far is the meteor after 10 seconds, and if it has 0 distance, it means that the meteor is at the Earth. Right, so we're substituting that in. We have 0 for t, and then we have 6,000 minus 600 times by 10 minus 0.2, 10 to the power of 3, and then plus 2 times by 10 to the power of negative 3, and then times by 10 to the power of 5. Okay, so if I work this out on the calculator, we have 6,000 minus 600 times by 10, that's just also 6,000 basically, minus 0.2, and then times by 10 to the power of 3, plus 2 times by 10 to the power of negative 3, times by 10 to the power of 5. Okay, so that is what we suspected. It is then going to be 0 meters, and that then shows that there will be a collision there. Alright, so for C, determine the acceleration, the rate of change of velocity of the meteor at 5 seconds. Okay, so basically we already have the equation for velocity. That's the first derivative. So if we now need the acceleration, which is the rate of change of the first derivative, we need to get the second derivative. So that means the second derivative, or the derivative of the first derivative, is then equal to, so multiplying this together, we've got minus 1 comma 2t, that the constant falls away, and then 4 times by, so plus 4 times by 10 to the power of negative 2 t to the power of 3. Okay, so that is then our equation. And now if we want to find the acceleration at t equals to 5 seconds, we're simply going to substitute in 5 into this formula. So minus 1 comma 2 times by 5 plus 4 times by 10 to the power of negative 2 times by 5 to the power of 3. Okay, so let's put that onto the calculator. We have negative 1.2 times by 5 plus 4 times by 10 to the power of negative 2 times by 5 to the power of 3. Okay, so that gives us negative 1. And this is in meters per second squared. So minus 1 meters per second squared. Alright, so question 36.1. A shopkeeper finds the number of people visiting his shop at any moment during the 10 hours that the shop is open is represented by NT. So where N is the number of people in the shop T hours after the shop is open. So meaning if I substitute in any value for T, that's let's say 5, then after 5 hours that would give you the number of people that is in the shop after 5 hours that it's been open. Alright, so for A, how many people in the shop open? So when the shop opens, that's another question like we saw previously where they asked immediately or directly, where T equals to 0 basically. So we basically just going to substitute in 0 for T equals to 0 cubed minus 12 times by 0 squared plus 36 times by 0 plus 8. Alright, and all the terms that are multiplied by 0 falls away, and we're simply left with 8 people. Alright, so that was easy enough. Then for B, at what stage is the number of people in the shop increasing? Okay, so once again, think about this practically. Rates of change is the first derivative, and we can also determine where is our value under question, or in our case our number of people, when is it increasing, when is it decreasing, because if you get the first derivative, like the first derivative, and then determine where is it greater than 0, that would tell you when is it increasing. So first derivative is equal to 3t squared minus 12 minus 24t plus 36. Okay, so the equation that we want to solve is where is the first derivative, because they're saying it's increasing. Where's the first derivative greater than 0? Where is it increasing? So we're just going to say, okay, 3t squared minus 24t plus 36. Where is it greater than 0? And we solve for this inequality. Now, to simplify this, I can divide everything with 3. Then I get t squared minus 8t plus 12 greater than 0. And at this stage, I need to factorize. So if I factorize this, I get what factors of 12 can give me 8. So 2 and 6. So if I say t minus 2 and t minus 6 greater than 0. All right, and now to find the inequality, we know the roots. The roots are where t equals to 2 or where t equals to 6. And this is an equation, if I represent this graphically, this is a quadratic equation where my roots would be at 2 and 6. So where is it greater than 0? And if you can't do this, remember just to go and recap on inequalities. Where is it greater than 0? The graph is greater here and here. So meaning the applicable values will be over there and over there, where the time is less than 2 or greater than 6. In other words, if the shop's open only for 10 hours, then it means that the number of people are increasing from 0 to the, can say equal to 0 up until the second hour, but not equal to 2, because the inequality just says greater than 0. At 2, it's actually stable, or it's increasing from 6. From 6 less than t less than or equal to 10. So we have to put in a normal inequality, we wouldn't have had these restrictions from 0 to 2. We just say t would be less than 2 or t would be greater than 6. But in this case, because the shop actually is only open for 10 hours, from 0 to 10 now, only that's applicable time. So that's why these questions, you need to think about them practically as well and not just apply the maths to it. Okay, so question 36.2. A particle moves along a straight line, the distance s in meters of the particle from a fixed point on the line at time t seconds is given by st. Right, A. Calculate the particle's initial velocity. Velocity is the rate of change of distance. So this one is pretty straightforward. To get the rate of change of the distance, we need to find the first derivative of our given equation. So this is then going to be 4t minus 18. Okay, that's basically it. Then the initial velocity is where t equals to 0. Initial is the start, so we substitute in 0 at 4 times by 0 minus 18, and that gives us a negative 18. Now this is in meters per second, so meters per second. Okay, then for B, determine the rate at which the velocity of the particle is changing at t seconds. Now we have the rate of change of velocity, which means now we just need to take this first derivative and derive it again. So the second derivative is then equal to 4. So that's going to be a constant meters per second squared. And that's it. So question 36.3. An industrial process requires water to flow through its system as part of the cooling cycle. Water flows continuously through the system for a certain period of time. The relationship between the time from when the water is flowing and the rate at which the water is flowing through the system is given by this equation, where t is measured in seconds. All right, so this is the rate. What is the initial rate of water flowing through the system? So don't let this confuse you by, if they say rate, in this case, we're not going to find the first derivative. This is the actual rate. They're already given us the equation, which is the rate. So we're not going to derive that one. We're just going to say, okay, initial rate, meaning where the time is equal to 0. So substituting in 0, we get negative 0,2 times by 0 squared plus 10 times by 0, and that basically gives us 0. And it doesn't say, oh, measured in seconds. Okay. All right, so B, after how many seconds does the water stop flowing? All right, so in this case, we want to know where the rate is equal to 0. So what we want to find is where this is equal to 0. So minus 0,2 t squared plus 10 times by t equals to 0. And then solving for this, we just substitute, we factorize. So if I take out t, factor out t, then I'm left with minus 0,2 t plus 10 equals to 0. So t is equal to 0, or t is equal to negative 0,2 t is equal to negative 10, and then t is equal to negative 10, or 10 divided by 0,2 is equal to 50. Okay, so 50 seconds. So this is 0 because that's where it started, but this is where it stops flowing at t equals to 50 seconds. Question 36.4. The displacement S, the distance from a fixed point of a moving car towards a fixed point after t seconds, is given by S. Determine an expression for the velocity of the car, the rate of change of the distance with respect to time. Okay, so velocity is just the first derivative, so we're going to say, okay, in this case I'm just going to say, okay, ds dt equals to 3t squared minus 18t plus 24. Alright, then that is then the rate of change, and then B, calculate the time t during which the car was reversing. Okay, so once again, practically thinking about this, if the distance from a certain point, if I just draw this here quickly, let's say this graph would look something like this, right? Then the distance from a certain point, so this is your distance, and this is where your point is, and then the car is going forward when the graph is going upwards. The car is going forward, but when the graph is going down again, the car is coming back again to that same point, and this is then your time. That's why it's in 2 dimension, but the car is actually moving in a 1 dimensional, but because you have time with that, it becomes 2 dimensional. So the car goes from the point, and then when it comes back to the point, the graph is decreasing again. So basically all this is asking is, where is this function of yours decreasing? And we do that by finding the first derivative, and then finding out where is it going to be negative, where the first derivative is negative, because remember, wherever the graph is increasing, like here, the first derivative is greater than 0. But whenever the graph is decreasing, the first derivative of your function is less than 0. And here again, your first derivative would be greater than 0. So basically, what we want to do is just find out where ds dt, this is just a different notation, is going to be less than 0. So once again, we're just going to solve for that 3t squared minus 18t plus 24 being less than 0. And I can divide everything with 3 to simplify. Then I get t squared minus 6t plus 8 is less than 0. And then t minus 2 and t minus 4 is less than 0. So t is equal to 2. And this is the roots now, because this is an inequality. So at t equals to 4 and t equals to 2 and t equals to 4. All right, and once again, this is a a quadratic graph, so if I'm going to represent that and it's positive, so I'm just going to draw it like this, where your two roots are 2 and 4. And where is it less than 0, meaning where's my graph below the x-axis, is this part over here, which then means that the applicable domain that I'm interested in is from 2 to 4, but not including, because it says less than 0. So the answer then would be from 2 less than t less than 4.